You just use the basic principles of QED, quantum electrodynamics, with quantized fields. Right? Okay, now sort of a new topic, linked, of course, with spontaneous emission. Photons just spontaneously being emitted from your quantum system, and that spontaneous emission plays an important role in thermodynamics and statistical mechanics. Now, most physics departments would teach a course, maybe two even, on statistical mechanics at undergrad level. I'm trying to remember what. I think I did my first, way back when I wasn't even 20. So I must have been second year undergrad. So yes, so undergrad courses at second and third year levels. Now that was in the Australian system, which is equivalent to the British system. So with a 3-year bachelor, in America it's a 4-year. So for if you're American, or if you're familiar with the American education system, that would be, say, junior level, your first statistical mechanics course. Now, if you have not studied statistical mechanics at all, then probably a lot of this will just go over your head. You won't have a clue what I'm talking about. If you have studied it, then it'll be a bit of revision, and you'll be able to link familiar ideas from statistical mechanics with quantum mechanics of spontaneous emission of photons, electromagnetic energy, quantized fields, quantized electromagnetic fields, photons. Right? Now, from statistical mechanics, one of the dominant figures, intellectual figures in that field is Boltzmann, of course. He really believed in the existence of atoms, and a lot of his colleagues did not. And this was before Einstein came along in 1905 and proved, with his Brownian motion mathematical analysis, that atoms do exist. Einstein's miracle year, 1905. He came out with a string of papers, each one in its own right, utterly revolutionary. He came out with 4 or 5 of them, all in 1 year. I think there's a Latin term for that. Annus, the year. Mirabilis, miraculous year. Okay, so Boltzmann came out with the so-called Boltzmann law. Boltzmann was trying to derive the proportion of particles in a gas, for example, of a given energy. Now, they weren't all the same. They didn't all have the same energy. That would be extremely unlikely, given their collisions, and some would gain energy a bit and some would lose. So you have a distribution of the energy these particles would have. And so if, let's say you've got an energy level M, or we'll call it EM, right? And N is, I guess, the proportion of particles that have that energy. And K here, you're talking about energy level K, dk. And so Nk would be the proportion of the particles that have that amount of energy. And he found that these N's here, using a mix of plausible, reasonable physical assumptions and just probabilities, probability theory, and a bit of calculus. By the way, I will teach a statistical mechanics course at undergrad level because the same reason as all the other dozen or so undergrad courses that I'll be teaching is that you need the background knowledge if you're going to teach yourself to a high-level graduate. If you don't have the foundations coming from undergrad courses, you'll be stuck. So I will be teaching undergrad level statistical mechanics. Anyway, so Boltzmann found a formula for this N, the proportion of particles having this energy, and he found that n was proportional to an exponential term to the minus the energy. So in other words, the higher the energy, the smaller the proportion of particles having that energy, and it sort of dropped off exponentially. Okay, so then the proportion of these two, now you're starting to get links with the quantum mechanics, K being your initial state and your transitioning. Now, remember, that's the theme of the whole chapter, transitions. So, so you start in state K and you transition to state M. Now from classical statistical mechanics, these energy level M and energy level K, this is what you get. You just you're dividing here, so you divide here, and all the constants, proportionality, whatever that were here, just cancel out because you've got above and below the same. All right. Right. Now, again, classically, if there's no spontaneous emission, so we're linking now. I was just saying before, classical mechanical, statistical mechanics, and spontaneous emission. So now, if there were no spontaneous emission, according to the text, then these two should be equal. That puzzled me. I didn't find that obvious because it seemed to me that these would be different because the energy levels are different. See, n is proportional to this exponential minus energy level. So I didn't follow that. If you do, fine. Anyway, okay, but again, this is statements by the two authors linking quantum mechanics, spontaneous emission, with statistical mechanics. There's this important link. Okay, but when you get this additional phenomenon of spontaneous emission of then that will imply I'll just give you the next line or two of the next session, but then the emission of radiation, that means energy is being released, right? So that means the majority of those systems will be in the lower energy level, to conserve energy, more or less, because you're emitting energy, and so the systems that are a consequence of that spontaneous emission of energy, they will have lower energies. Okay? All right, I'll just continue on with the next session, and we can bring in we'll bring in this quantum mechanical formula.